Okay, and so now I'm going to move over to the power systems of the Bubolaq, and the one I'm going to really focus on today is the nuclear power systems, though the colony itself will use a combination of nuclear power, solar power for electric production, and solar thermal power to supplement the central heating system of the colony. And so this design is based around the M-Power reactor design, though it is intended to be a fungible placeholder for any small modular reactor. And so we're looking at about 360 megawatts of electric power, which yields a gigawatt of thermal power during production. And this is particularly beneficial on Mars, where at the latitude that we're talking about, we'll need a surplus of thermal capacity to heat the greenhouses, particularly during the winter. But the domes themselves will be built within the aircrete foundation. For the domes, there will be an embedded thermal salt heat loop that will help transfer heat around the colony to central reservoirs, which will then convert it to a lower operating steam-based system for the domes themselves. So this is beneficial because it also provides a redundant ability to purify and filter water on site for the dome, and it has a good passive sterilization capacity because autoclaves are able to provide medical grade sterilization. So access to that for all domes will be part of the common infrastructure of the Bubolaq colony. All right, so a few notes about the M-Power reactor is that it is a system that is, even though it's one of the earlier designs for small modular reactors, it is specifically geared towards a lot of the automation that is particularly prevalent in later designs like the NuScale modular reactor system, which is the primary commercially available substitute that I would recommend per the specifications that are in the Bubolaq design paper. So one of the great benefits and what is actually absolutely necessary about this centralized digital management system for nuclear reactors is that this is one of the most labor-intensive pieces of equipment that is going into this colony design. So a typical reactor of this size would have over 200 people operating it, and the budget for this colony design is roughly 120. So this is within both what Babcock's and Wilcox and NuScale have proposed for these digital management systems. And given that the design here is at 2037, it's definitely within the targetable range. But this is one of the more critical pieces of technology, so it is assumed that it would be going in much earlier in the process. So as with the tunnel boring machine, though, these are very heavy pieces of equipment. And so unlike the tunnel boring machine, it's not something that there is a great substitute for in terms of power capacity. We'll get into solar in a few minutes here, but long story short, it would need to be broken into a few pieces. So we're talking about 600 tons or so for each of the individual reactor units, and even with the ability to cast some of the bulk metal containment vessels in situ on Mars, which is in and of itself a technical question. There is the downmass capability on the surface of Mars. So it's assumed through this design that you would be looking at either multiple components maxing out at roughly 100 tons in order to use the Starship architecture, or you would require a dedicated landing vehicle, assumed to be in the 200 to 300 ton range at the surface of Mars. Okay. And so one additional note about these is that these would use highly enriched uranium or a similar fuel, requiring a regular refueling cycle. So specifically within this design, I've left aside some space for technicians who would be required to cycle in and out at a 6-year refueling time frame. But part of the benefit of this design, though, is with the other power systems and with the integrated heat and battery power storage systems, this is designed to be somewhat oversized for the 1,000-person scale, to the point where one of these reactors would be able to go down for a year, covering a Martian winter at least, in order to be refueled. All right. And so one of the other power systems that will be necessary throughout the colony is a smaller source of incident power for industrial manufacturing and other high demand power situations. So again, water purification is something that might be within that realm, but also as a buffer capacity for part of the grid. So nuclear is not known for its reactivity, but something that is a much smaller system like the pylon reactor design from the Ultra-Safe Nuclear Corporation has a much greater ability to respond to grid demand in just the sense of daily cycling. So these reactors are currently being deployed in Canada as a standalone power supply for off-grid installations. They operate at about 5 megawatts each electric, which offers about 20 megawatts thermal, if appropriately configured. And one of the great parts about the Ultra-Safe Nuclear Corporation is they're very actively interested in space. They currently have a design for a 1 megawatt reactor that is intended to be used on the moon, but they have noted specifically that their design can be modified for Mars as well, where it will have better performance due to better conductive cooling potential. Sorry, convective cooling potential. All right. And then a smaller but also quite useful system, particularly for remote installations or as just a dedicated source of energy for high load installations, are heat pipe reactors. So these are operationally currently in the up to 10 kilowatt range, but there are designs for up to 1 megawatt heat pipe reactors. So similarly, you're looking at 4x heat production with each of these reactors, but these are intended to be for your remote installations and for anything that would require a much more incidental power source. So the benefits of the kilowatt power design are that it is tunable, unlike most other nuclear reactor designs. And given the fact that it uses a low enriched uranium, it does not have the potential for a meltdown, and it can safely overload itself, or it can safely shut itself off in the event of an overload. Okay. And so one of the technologies we're specifically looking to maintain with a lot of this power infrastructure is a robust chemical processing industry. So this has to be one of the earliest industrial applications that we focus on Mars, specifically because of the capability that it gives to the colony. Plastics in particular are one of the larger components of this, but that is primarily in the end user sense and the finished goods side of things, because the industrial reagents, in terms of acids for processing regolith and just other things that are going to help along the production process, are necessary on Mars. As we mentioned, it's $500 a kilogram to import that, and if we could instead just use locally derived duckweed to produce, say, oxalic acid instead, it is a very motivating situation. And so one of the most notable things that we will be producing is methane. So the Sabatier reaction is well known, and we'll definitely be looking at that. But there are a number of other uses for that other than just rockets that I kind of wanted to touch on for a second, and just point out how this capability that we'll be achieving through a robust chemical manufacturing industry will really enable other strengths within the colony. And so one of the bigger things that I think is not a part of discussions about early colonies is how domestic transport is going to strongly amplify the capability of the colonists themselves to explore and really connect with the surface of Mars. And so this is one area where methane could be a very interesting fuel source. So just given the higher energy density and the minimized impact of thermal variability on it as a fuel, it offers a compelling alternative for domestic transport vehicles, but also as an emergency power source. So the Sabatier reaction can be run in reverse to very efficiently generate power, and this is an existing commercial option for off-grid installations. And so one of the other great things that this chemicals industry is going to really promote is the ability for in situ fabrication of more complex goods. So these are things that would be on the marginal side of transport costs, but that given a robust infrastructure, our colony could produce very easily and with low personnel input. So there are already thriving networks on Earth of plastic-based 3D printers, but particularly as the metal 3D printing world expands a bit, that capability is going to be something that will be directly available to consumers for finished goods, but also within the colony itself to help support any needs that individual enterprises might have. So one additional note that having a cheap fabrication industry really promotes is that within this colony, we're expecting that these 1,000 individuals are there to stay. So these are people who have dedicated themselves to the cause of living on Mars and are really in it for the long haul. And as a part of that, it's very important to offer them both creative outlets, but the ability to engage with a society and a culture that derives itself from the naturally available resources. And fabrication is really at the root of that. So it allows for the ability of more refined goods, whether it be in the sense of media arts or capabilities, so the ability to produce ceramics or glass as an art form, but also as a jewelry that can then be part of the commercial market. And then stepping back to the industrial side, a lot of what this custom fabrication industry on Mars is going to help us do is maintain higher level technologies. And so one of the most critical aspects of this is a very large network of semi-autonomous and autonomous drones that will be the backbone of our in situ resource production. And so drones are a great way to really limit the danger for humans on Mars. So one of the biggest dangers that I mentioned earlier is galactic cosmic radiation. And so a lot of work that needs to be done on the surface, the risk for this radiation exposure could be minimized through the use of drones. So it's on Earth, we already have the ability to remotely pilot these drones, and with a VR headset, really feel like you are in that situation. And this is one of the mechanisms that I strongly propose be used on Mars to limit the danger to workers throughout their day. But it's also a way to offload services within the colony itself. So most of us have ordered food through a delivery service, and one of the great things about Mars is that that should still be available to you. It's just very likely going to be a drone dropping things off rather than a driver. So this gets a bit more fundamental too, in the sense of offloading a lot of the labor involved in agriculture. So there is a project at Harper's University or Harper Adams University called the Hands-Free Hectare, where they are essentially using a combination of these autonomous and semi-autonomous drone systems to plant and harvest an entire hectare of, believe it is wheat. Sorry, not sure on that one. Just as a demonstration project to show how this is possible. And I think that it's instrumental that we see these types of projects in more diverse environments before we get to Mars itself. And so our image on the right here is one that you may recognize, may not recognize. The yellow base here is the Boston Dynamics Spot robot, but this is just to illustrate that a lot of the drones that we're familiar with might be used in more diverse ways as well. So this is a set of robotic arms that have been put on Spot to help him act more as a waiter, and again offer some of the creature comforts that we're familiar with here on Earth, one of those being dining experience that could be facilitated through robots to help avoid the need for human personnel to staff those positions. Another one of those might be a drone mail system, where the use of small drones for interior flight would really help with the transport of goods between individuals within domes. And so we've talked a lot about them, but let's take a bit of a closer look at those domes themselves. And so we'll be looking at a large number of domes in a large number of situations within the Bubolaq itself. The majority of the domes for habitation are going to be larger and then subdivided into living spaces within them. So we will have a dome like this, as you see. So the dome that you see on the screen here, you can imagine that each court might be subdivided into an apartment block for a large number of individuals. But domes already exist on Earth up to a hectare in size, and so we'd be looking at large domes like that to help instill a sense of community and togetherness within the Bubolaq. Though it's important to note 1 hectare is not, well, it would be big enough for 1,000 individuals, but we're going to go a bit lower density than that to also help provide a bit of comfort for the residents of Mars. So there is a sense that individuals within the colony themselves will be physically separated and may not be living in the same environment. And this is both good and bad because it offers the ability for individuals to change their living situation voluntarily and to regions that they find more desirable. But it can also create subdivisions that divide the colony from feeling truly unified. So these domes will be PVC and polyester, which are both domestically producible, and they will be, as I mentioned, built on an aircrete foundation to help thermally isolate them from the ground, and they will cycle the air with the internal cavern to help balance what is needed within the dome itself. So some domes might be built in, or some domes for the agricultural system will be built with more transparent tops, but it's important to note that not all domes will be built to the same specification. So it requires a much thicker amount of material to shield a dome from radiation than it does to contain atmospheric pressure, even if you're talking about a differential to the Martian atmosphere itself versus to the Bubolaq cavern. And so for that, agricultural domes will need to be a little bit thicker, also to help them withstand the weather effects of being on the surface itself. But it's important to note that they will likely not be thick enough to provide full shielding from galactic cosmic radiation. So, as mentioned, this is another great reason to heavily employ drones because it's going to limit your time within the greenhouse, which is in itself a dangerous environment, despite being able to walk around in potentially shirt clothes. Yes, and there are other factors why you might want to stay out of the greenhouse that we'll get to in a few moments. But so while I mentioned that large domes are available, there will be a very large diversity of domes that you'll see. So some of these might be smaller, and you can see within the cavern the ability to purchase and install private domes that could then be dedicated towards their own specialized uses. So the one on the right here is set up as a small shop, but you might also see enterprising Martians setting up their own construction company and using something like a dome here to provide a secondary environment on the surface that can then be utilized by other colonists. Okay. So these domes will also help provide space for a key feature for the Martian colony that's going to be necessary at 1,000 people, and that's a thriving healthcare industry. So Mars is very far away, as many of us might be aware. It is currently a 6-month travel time between the Earth and Mars, and the ability to get this travel time below 3 months is not readily apparent on the horizon. So with that being said, it's important to have all capabilities available to the Martian population in order to prevent conditions that we currently see as treatable and not a concern from becoming very large health risks on Mars. And so this is minor organ failure and or removal and the need for life-saving surgery. So to that end, of the 1,000 individuals on Mars, we're looking at least 80 healthcare individuals in specialty. So this would be people who are employed full-time in the healthcare industry of Mars. And part of this is necessary in order to have the capacity if there were ever a traumatic event. So one of the big critical factors behind the size of a healthcare network is that in the event, so with the activity of mining, we might expect any traumatic event to be accompanied by multiple injured Martians. So for that end, we need to be able to operate multiple trauma care units in parallel. So the use of laparoscopic robots is something that can really help to make these surgeries a bit safer and also to help with throughput in the healthcare system. But beyond that, we're looking at a number of different technologies that will also help to preempt a lot of conditions that might be troubling on Mars. And so one of those is pervasive monitoring. So adding a heart rate and a urine analysis monitor, or making available a heart rate and urine analysis monitor for every citizen, would target a number of conditions before they became more problematic and would allow us to potentially use that 3 to 6 month window to send someone back to Earth should their condition prove to be beyond the capacity of the Martian healthcare system. In combination with that, though, is going to be a lot of environmental monitoring and preemptive action towards environmental concerns, specifically towards known disease reservoirs like agricultural animals or products. So with that, we would also be very interested in looking at phage panning as a way of producing a response to endemic microbiological concerns. So this is particularly in the sense of environmental contaminants that we would be monitoring, and this could be used in the agricultural system as well. But phage panning is a way to rapidly produce a viral response to a specific bacterial pathogen within the environment. So if there was something that we were unprepared for within the agricultural or healthcare system, this is a way for us to respond to it in real time. And there are a number of other reasons we'd want to maintain bioproduction capability, specifically for the production of antibiotics and a number of other compounds that would not last long, given the transit times from Earth to Mars. All right. And so part of this pervasive monitoring is going to be enabled through the data network of the colony infrastructure. Excuse me. And so Mars will have a connection to the Earth-based internet system based on a series of relay satellites orbiting the planet, but it will also have its own planetary internet network. So